Hello and welcome to BBC Learning Zone. Tonight, GCSE exam revision looking at chemical reactions and structures, the periodic table, industrial processes, geological changes and changes in the atmosphere. All that plus exam tips from Katie Hill, Alice Beer and Corrie's Tracy Shaw.
Hello and welcome to GCSE Bite Size, the series designed to give you the edge when sitting your GCSE exams. The Bite Size Science programmes will give you loads of help with your science award, but this one specifically focuses on the things you'll need to know for the chemistry part of the exam. The other two programmes focus on physics and biology. If you work your way through all three videos, you'll be sure to improve your grades. Most students take double award science. This means that you'll get a double grade for science. DD, for example, or CC. You need to know all the work in this programme for the double award science. There are two tiers of examination in science. Students taking the double award foundation tier exam can achieve grades between double G and double C. Students taking the higher tier papers can gain grades between double D and double A star. You must make sure that you're entered for the correct tier, and when you get to the exam, make sure you're given the right paper. The work in this programme that will appear on the higher tier papers only is marked with an H icon. You can tackle each tape in bite-sized chunks, or if you really want to go for it, you could sit down and do one subject tape at a time. The programme stands alone, so you'll get a lot of really useful information. However, if you combine it with the book, you'll get exercises that go with the programme. And there's more. If you go to our unique online site, you'll find the key content for your syllabus, exam questions to practice, and animations to help you with difficult concepts. There's also an online link to teachers who'll answer your questions. Whenever there are direct links with the book or with the online exercises, you'll see these icons on the screen. There are 6 main sections in this programme, each one lasting about 20 minutes, and each one covering an important part of the chemistry element of the science syllabus. If you like, you could fast forward to view the section you need the most help with. The clock on screen will help you keep track of where you are in the programme. Whatever you do and however you do it, the aim is to improve your knowledge and confidence for your coursework or exam. In order to have a better understanding of chemistry, it's important to have a good imagination and to be able to picture in your mind what particles and atoms are doing. This will make it surprisingly easy to remember things. This section about mixtures will help to explain 4 important terms: solute, solvent, solution, and soluble. Remember, they all start with SOL. Pause the tape here and write your own definitions. Then play on to compare your answers. You should have noted down the following definitions. Solute, the substance being dissolved. Solvent, the liquid which does the dissolving. Solution, the solute dissolved in the solvent. Soluble, if a substance dissolves in a solvent. In chemistry, mixtures often need to be separated or purified. There are several ways to separate mixtures. For example, to get pure salt from rock salt, you need first to dissolve it in water, filter it, and then evaporate it to get salt crystals out of the filtrate. Filtering and evaporation are examples of separation techniques. While you're watching the first two clips, pay particular attention to what happens when substances dissolve in water. In this case, salt, and then sugar.
What's happening out there?
We're doing an experiment. We want you as a witness.
2 identical beakers of water, 2 identical piles of salt.
So the scales balance. But what will happen if I put this salt into the beaker?
That salt will go down, won't it? It will be heavier. There'll be more weight with the salt in the beaker.
I bet it'll go down at first, but then go up again.
No, you're both wrong. This side will go up because there's 2 things on that side and there's only 1 thing on this side.
Go on then, let's see. But they've still balanced. Why? Stella, can you try this?
Okay. The same thing happened when I tried it. They still balance because the salt is still there. It weighs the same when it's in the water as when it's in a pile next to it. But something else is going on here. Take a closer look at your experiment now.
Look, the salt's gone, but the scales still balance.
So even though you can't see the salt now, it is still there. But just what has happened to the salt to make it vanish?
Watch the next clip, then stop the tape to see if you can do the following exercise. 1. Draw a diagram to show what's happening to the sugar particles. 2. Write an explanation of the process.
I know something that's really soluble in water. Sugar.
Stop! It's full! It'll overflow!
No, it won't. Stella, what's going on?
Okay. How come we can add something to a mug that's already full and it doesn't overflow? To understand what's happening, you need to know exactly what's going on when something dissolves. You need to look at it really closely. Imagine you had an eye more powerful than the most powerful microscope. What might you see when sugar dissolves in water? The water itself is made up of many tiny particles, all moving around randomly inside the container. The sugar is made up of bundles of sugar particles called crystals. When the sugar dissolves in the water, the bundles of particles which make up the crystals break up. They become completely mixed with the particles of water. All the particles move around freely and the whole solution behaves as a liquid, so you can't see the sugar. The sugar particles move around in the gaps between the water particles. There's room for them to slip in between. This means the volume of the solution does not increase that much when sugar is added. So you can add more than you think before the glass overflows.
So, how did you get on? Here's what you should have included in your answer. For question 1, the diagram should look like this. Particles within a liquid are in contact with each other. The forces between the particles allow movement. For question 2, the sugar particles must first break up and mix to fill in the gaps in between the water particles. The volume of the liquid does not change. Now that you're familiar with the words solute, solvent, solution and soluble, you'll need to know the differences between them. Note them down during the next clip.
Meanwhile, I'm investigating something that doesn't dissolve in water. Nail varnish. It's insoluble in water, but it will dissolve in a chemical called propanone, also known as acetone. A liquid that will dissolve something is called a solvent. The propanone becomes green too, a solution of propanone and nail varnish. This dye will not dissolve in water, the most common solvent. In fact, however much I stir it, it won't mix at all. But ethanol is a solvent. Look, the solution is coloured but clear. You can see right through it. Clay won't dissolve in water. It's insoluble. It mixes with it, but no matter how much I stir, the mixture stays cloudy. This is how we know that something hasn't dissolved.
You should have noted down that the solvent is the liquid in which things dissolve. The solute is the solid which is being dissolved. The solution is the solute dissolved in the solvent. Soluble means that the solute dissolves in the solvent. So why is it that some substances dissolve in water but others don't? Pause the tape and try to answer the question. A good answer would include the following. Substances will only dissolve in solvents that are similar. Propanone and nail varnish are similar, so the nail varnish will dissolve in the propanone. Many different substances dissolve in water. When no more of a substance will dissolve in the water at a particular temperature, it's called a saturated solution. You need to understand these key words: saturation, crystallization, and solubility. Pause the tape and come up with your own definition for each of them. To check your answers, play the next clip.
A strong salt solution is being prepared by Diane, who works here. But soon the salt stops dissolving.
So much salt is dissolved that it can't dissolve anymore.
Exactly. That's what we call saturation.
Right.
If I was to take this solution and pour it into this beaker right here, and we was to leave it in the sun for a while, it would eventually evaporate and we would have crystals left.
Starting with a saturated salt solution means as soon as any water evaporates, the water that's left can't keep all the salt dissolved. So, salt crystals appear on the string. Under the microscope, you can see this happening. It's called crystallization.
The same thing is happening on these ponds, but on a much larger scale. The sun heats up the water and it starts to evaporate, leaving the salt solution to get stronger and stronger. Eventually, it becomes saturated. The water just can't hold any more salt in the solution, and the salt starts to crystallize out.
The amount of salt that can dissolve completely in a given amount of water is called its solubility. This much common salt, or sodium chloride, will dissolve in a litre of water. This is another salt called magnesium chloride. You can dissolve this much in a litre of water before the solution is saturated. Magnesium chloride is more soluble in water than sodium chloride.
Having seen the clip, you should now know that a point of saturation is reached when no more solute will dissolve in the solvent. Crystallization is the forming of crystals when water is evaporated from a solution. And solubility is the amount of substance that will completely dissolve in a given amount of water at a given temperature. See if you can answer these questions about dissolving. Why is there saturation? Why is magnesium chloride more soluble than sodium chloride? Pause the tape and have a go. Remember, you can replay the clips if you need a reminder. In your answers, you should have explained the following. The spaces between the particles are full if the solution is saturated. Magnesium chloride particles can fit into the gaps more easily than sodium chloride particles. It's essential that you know the separating techniques off by heart for your exam. The clip coming up will help you to revise them. Pause the tape here and test yourself by writing down the 4 you have seen so far. The 4 separation techniques you have seen so far are crystallization, distillation, evaporation, and filtration. A good tip to remember is that they start with the letters C, D, E, and F. Watch the next clip, then stop the tape to answer the following questions. 1. How is clay separated from salt? 2. How is salt separated from a solution? 3. You should be able to draw a labelled diagram of the processes used in the clip.
I'm on another mission for salt, but this time my salt is 150 metres underground, here at the Winsford Mines. It's the only rock salt mine in the UK, and it's enormous.
The rock salt found down here is a mixture of salt and clay. The rock salt found underground in these mines varies quite a lot. Just take a look at these samples. The whitish one gets its colour because it has a very large proportion of salt in it compared to clay. The middle one has a bit more clay in it, although it has got a lot of salt still. And the darker one has even more clay than the rest. My task is to find out exactly how much salt is in one particular sample. But first, I've got to separate the salt from the clay. Round the corner, there's someone to help me. Hi, George. Yeah, I've collected my rock salt sample for analysis, so what do I need to do?
Well done, Trish. You've put the rock salt nicely on the weighing paper.
Lovely jubbly. Take 100 grams of fresh crushed rock salt. Add water and mix well for 2.5 hours. The salt dissolves, but of course the clay does not. Pour the mixture through a filter. The clear salt solution passes straight through into the flask. But the brown clay particles are too big to get through the filter paper. Heat the salt solution. The water evaporates, but the salt is left behind. By subtracting the weight of an identical empty beaker from the weight of my salty one, I can calculate I have 94.8 grams of salt.
Remember the questions you were asked before the clip. Stop the tape now and have a go at answering them. You should have worked out from the clip that 1. Clay is separated from salt by dissolving and then filtering as clay is insoluble in water. 2. Salt is separated from a solution by evaporation. Water is evaporated, leaving behind salt or sodium chloride. 3. Look at the diagram and compare it with yours. Another way of presenting the same information can be in the form of a flow diagram. Here's an example showing the extraction of pure salt from rock salt. It illustrates the sequence of events in the extraction of salt, as well as the different separation techniques. It's important for your exam that you're able to read a flow diagram. This is the end of the first section on mixtures. Play this section as many times as you like until you feel confident about the processes involved in dissolving and separation techniques.
I used to panic when I get to a question and I can't answer it, and I used to sit there and struggle onto the one question rather than go ahead and carry on with the other questions and then go back to it. So my advice is to carry on and go through all the other questions and then go back to the difficult ones.
When you're revising your work, make sure you do take a break. Relax for an hour or 2 hours or 3 hours. You will get your work done and you'll pace yourself and you'll feel so much better afterwards.
If you do double science, remember it's worth 2 GCSEs, so you should do twice as much revision than any other subject.
Set yourself a sensible revision plan, and each time you complete a topic, treat yourself to a treat, like a favourite chocolate.
Think about the examiner. She's marked loads of scripts before she gets to yours. If yours is neat, tidy, easy to read, then she's going to be much happier and much more likely to give you some marks, isn't she?
A good way of revising chemistry in soluble salts I found when I was revising was, as it goes like this. Hydroxide and carbonates won't melt away, but there are some exceptions whose names we now say. Sodium, potassium and ammonium too, they're unlike the others dissolve, yes they do.
Well, I find when I'm trying to memorise things, you know, because I'm 500 years old, yeah, what you want to try and do is narrow things down. Yes, yes.
Narrow it down.
Narrow it down.
Don't try to be concise.
Concise, keep it short. Keep it short.
It's very
That's
useful,
right.
isn't it?
Yeah, the smallest piece of information you've got to remember is always the best.
And they will thank you for that.
That's right.
Maybe you want to try some brain food.
Brain food.
Brain food, like
yes.
dog.
Or dog.
Dog.
Oh, for goodness sake, you're disgusting.
Sorry, Mr. Sage.
Yes. Bullet points, that's the key.
I'm Mr. Sage. I'm eating too much dog.
You'll see many chemical reactions in this section. A chemical reaction has taken place if one or more of the following has happened. 1. A colour change. 2, a gas is given off, indicated by fizzing. Or 3, a temperature change. Something new is always formed as a result of a chemical reaction. Pause the tape here and have a go at answering these questions. 1. What 3 things are needed to produce fire? Draw a fire triangle. 2. Write an equation for the burning of natural gas or methane. And 3. Is the reaction exothermic or endothermic? The following clips look mainly at combustion reactions, which are substances reacting with oxygen. You'll also see how rates of reaction can be affected. There's a lot of chemistry involved, and to get the most benefit, you may need to watch the section a few times and focus on different aspects with each viewing, such as evidence of a reaction taking place and how rates of reaction can be increased.
The flame is basically a chemical reaction between the air and the gas. It produces lots of heat and light and also waste gases.
To understand what's really going on in here, you need to get right inside the flame. Fire is a chemical reaction. The flame you see is what comes out of this chemical reaction. Gas is so hot that they're glowing. The chemical reaction happened between fuel, natural gas, and oxygen from the air. But to get the reaction going, it also took heat energy. These are the 3 things you need for fire: a fuel, oxygen, and heat energy. The chemical reaction produces more heat, energy which is useful. But useful not just to us, it also keeps this reaction going, so long as the fuel and oxygen keep on coming.
One of the jobs I have to do whilst I'm on shift is to take measurements inside the furnace. This involves removing a block from the side of the furnace and poking a probe in there. The probe sucks the sample from the furnace, sends it down a tube to an analyzer, which will tell us exactly what goes on inside the whole furnace chamber. We're trying to reduce the amount of pollution to the environment and also to increase the amount of heat energy that we produce and make the most of this energy.
3 substances you should have noted down that are essential to produce fire are fuel, oxygen, and heat energy. Remove any one of these and the fire goes out. An equation for burning of natural gas is methane plus oxygen equals carbon dioxide plus water. And the burning reaction is exothermic, as it gives out heat. Having established what is needed to produce fire, you then need to know how the speed of burning can be increased. Look at the next clip and jot down the 2 ways to increase the speed of burning. See if you can also write down 2 other ways of speeding up a chemical reaction not shown in the clip.
Sydney explained that the power of explosives comes from the speed of their chemical reactions. All the energy is released at once. It was time to open up the portable laboratory to find out what affects the speed of burning.
Sorry.
We started off with the fuel you use on barbecues.
Okay, I'm going to take a piece of charcoal, and we've got a flame which is a few hundred degrees. You can't see the flame very well because it's in the open air. You can see it's getting hot now. You may be able to see it's beginning to glow.
A lump of charcoal burns easily in air, but the reaction is quite slow because the vital oxygen can only get to the outside of the lump. But it will burn faster if you get more oxygen to it, say by blowing on it.
Well, we can see how it glows.
But charcoal can be made to burn much faster. Charcoal is the fuel in gunpowder, but even Sydney can't make gunpowder because that needs special equipment. It comes from the factory in little granules. Inside each one, the charcoal has been ground up very finely and then mixed with other chemicals which will provide all the oxygen. That extra oxygen makes quite a difference. In slow motion, you can see just how fast the reaction is. Some quite surprising things will burn if enough oxygen can get to them.
Now, here you have some steel wool.
Steel wool is the stuff people normally use for scrubbing saucepans. It burns quite quickly because oxygen in the air can reach right through it easily. The oxygen is vital. In a different form, exactly the same material, steel, just won't burn at this temperature.
I've got a piece of steel here. It's actually a nail. Now I'm going to heat this nail, but it's certainly not burning. No sparks. Very unspectacular. I think that you will agree that we could stand doing this for a month of Sundays and it's not going to catch fire. Frankly, I am becoming bored with this nail.
But even quite large pieces of steel will burn if you can get enough oxygen to them. It's a process that's used in industry. The flame heats the metal, but on its own, that's not enough to make it burn because there just isn't enough oxygen. Burning only happens when he sends a jet of pure oxygen through the flame. It's by far the easiest way to cut through steel this thick.
The two ways seen in the clip to speed up burning are 1. Increase the amount or concentration of oxygen. 2. Increase the surface area of the fuel. Two other ways to speed up a chemical reaction are 1. Add a catalyst. And 2. Increase the temperature. Rates of reaction can be explained using the collision theory. The more collisions that take place between the reacting particles, the faster the reaction will take place. Pause the tape and complete this table by filling in how the 4 ways of speeding up a chemical reaction can be explained using the collision theory. Compare your answers with the ones in the table. During the next clip, you'll see oxidation taking place. Copy this table and complete it by writing in the names of products of burning and say whether they are oxidized by the addition of oxygen or the removal of electrons. Pause the tape whenever you need to make notes.
Fires need oxygen. The more oxygen, the faster they burn. With liquid oxygen, they burn faster still. This biscuit is soaked in liquid oxygen. A piece of wood burns so well when it's soaked in liquid oxygen that it even burns underwater. But what happens if you can't increase the amount of oxygen? Aluminium foil won't burn, but if you grind it into a fine powder and blow it into a flame, it will. Lumpy custard? Powdered custard? Most substances, like hydrogen in this jar, need a flame to burn. Or do they? This is platinum, used as a catalyst. This can is filled with natural gas. As the gas burns off at the top, it's replaced by air coming in through the bottom, which mixes with the rest of the gas. Gas leaks at home are devastating when the proportion of air to gas reaches a critical point. There's a leaking cylinder of gas in this van, and there's a spark. Phosphorus has to be cut underwater, because if it's left in the air, it catches fire on its own. All burning reactions are examples of oxidation, because the substance that's burnt is oxidized. Burning substances are chemically combining with oxygen. The oxygen is an oxidizing agent. But the oxidizing agent doesn't always have to be oxygen gas. Potassium chlorate is a strong oxidizing agent. It's got lots of oxygen in it. You'll see the point of the coin later. The white substance is the potassium chlorate. Phosphorus dissolved in a liquid is added. When it's touched with a hot metal rod, during the flash, the phosphorus was oxidized by the potassium chlorate. The reaction was so ferocious, it was as if the metal plate had been hit by a sledgehammer. Reactive metals like magnesium can even burn in carbon dioxide, a gas which normally puts out fires. The magnesium combines with oxygen in carbon dioxide, coating the jar with magnesium oxide powder. The black specks at the bottom are carbon. But can things burn without any oxygen? This is sodium metal. It burns in air. But here, it's burning in chlorine gas. So if there's no oxygen, how has the sodium been oxidized? Sodium metal is made up of sodium atoms. Each atom has one electron in its outer shell. When sodium burns in chlorine, each sodium atom gives its outer electron to a chlorine atom. The same thing happens when sodium burns in oxygen. The outer electron is given to an oxygen atom. So more accurately, when something is oxidized, it loses electrons. Oxidation is loss of electrons.
Here are some of the products you may have written down. Aluminium burns to produce aluminium oxide. Custard burns to produce carbon dioxide and water. Methane also burns to produce carbon dioxide and water. Phosphorus burns to produce phosphorus oxide. Magnesium burns to produce magnesium oxide and carbon. And sodium burns to produce sodium chloride. Here's an easy way to remember the definition of oxidation. ORE stands for oxidation, removal of electrons. It's a shorthand version which should make it easier to remember. The opposite of oxidation is reduction. How would you define reduction? Pause the tape here and write down a definition for reduction. definition of reduction is taking away oxygen or adding electrons. This completes the second section. You should now feel more confident about ways in which you know that a chemical reaction has taken place and how the rate of a chemical reaction can be increased. You'll need to know all of the information in this section of the programme for Foundation and Higher Tier Science Double Award. Remember that the book and online exercises will also help. Finally, to end this section, here's a nifty way to help you remember the basic difference between oxidation and reduction. Oxidation is loss of electrons, reduction is gain of electrons, or oil rig for short.
I didn't get where I am today by not revising. I revised, but a very good tip, if you're going to revise, you can only revise if you've vised. So make sure that you vise first, and then you make your revising much easier.
Make sure that when you actually do sit down to revise, you're really focused, and revising is what you do. So make notes, focus your mind, because the amount of times I tidied my bedroom in one day when I was revising, it was shocking.
The use of patterns is important in chemistry. Learn those patterns and apply them. For example, the reactions of acids, or how to write formulas for alkanes or alkenes.
For the sciences, where there's a lot of work that needs to be practiced rather than learned, it is useful to write the particular formulae that you are practicing in bright colours on top of the page and practice lots of different questions in lots of different ways constantly, and that will sort of reinforce the formulae into your brain.
In chemistry, I find it useful to use word association. Like for remembering, oxidation is loss of hydrogen and reduction is gain of hydrogen. I use the word oil rig.
Before any show I do, I have to do a dress rehearsal, whether it's needed or not, because I know it gives me self-confidence and I know I've done the best I possibly can. It's the same with revision for exams. It is the most important thing in the run-up to your final GCSEs. The results you get make such a difference, and they can really change your life. I know. I only took them 2 years ago. Believe me, revise as much as you can. You know what results you want, and you know how well you can do. The most important thing I have left to say is good luck.
Materials are divided into different groups for different purposes. In this section, materials are divided into groups according to their properties. The key thing you need to do is relate the properties to their uses. Watch out for the following key word in the clip coming up, as you really need to understand it.
Professor Colin Humphreys is in charge of the University of Cambridge Materials Science Department. Colin, what does a materials scientist do?
Well, a materials scientist tries to understand the properties of materials, like how strong they are or how good electrical conductors they are, in terms of where the atoms are and in terms of the forces between atoms.
Yes.
If you can understand where the atoms are, their chemistry and the bonding between the atoms, the forces between the atoms, then we really know what the material will be like. It all follows from that.
The fact that gold is inert is another reason why we see it in temples and churches like this. Because it doesn't decay, it lasts for hundreds, if not thousands of years. And not only does that make it valuable, but it means it survives the centuries for us to see today. These religious buildings also provide us with another clue to a property of gold that's been known about and put to good use. In hot countries, temple roofs were often covered in gold, not only because it was an expensive tribute to the gods, but also because it reflected the sunlight, and so the heat, keeping it nice and cool inside. This property has been used by materials scientists to help them with some very advanced technology, particularly in an area where strong sunlight can be a problem, such as in space.
Well, gold is a particularly reflective element in that sunlight, when it impacts on gold, tends to reflect it at a fairly high rate. We can expect sun to reflect at 95, 98%. I think often you have a situation where you don't want your spacecraft to get too hot. So we'll put a gold surface on the outside to reflect the sunlight and to keep the spacecraft from getting any hotter than we'd like it to be. In other applications, such as the astronauts' visors, we may find gold laced inside of the goggles so that the sun reflects from the goggles and the astronauts can see without being blinded by the sunlight.
You got it. Extremely thin coatings of gold can also be used to reflect heat from the windows of modern office buildings. Applications such as this glass means that scientists are working with gold at the level of 1 atom of thickness. For this, you need very pure gold. I learnt a thing or two about gold and about its properties by visiting a refinery. Here, gold is taken through several stages of purification to be transformed from gold ore to pure gold bars.
Why is it that gold doesn't corrode? To find out, you need to look at the atoms of gold. What properties did these give to metals? The answers to these questions are in the next clip on the structure and properties of metals. Watch it carefully, then pause the tape to note down the answers.
So what is 1 atom of thickness? Well, this gold leaf here might look pretty thin. You can almost see through it, but it's actually 250 atoms thick. We need to look a little closer. Magnified by an electron microscope, these are individual atoms of gold. To help understand these images, scientists use models to represent the relationships between the atoms, the actual structure of the material. But what can they tell us about the properties? Now, I've got a battery here connected to a light bulb. If I close a circuit with this gold bar, if gold conducts electricity, then the bulb should light up. Yeah. By being able to look at gold